All right, guys. So we're on the topic of motion and straight line. We're gonna basically just practice some questions today. So we already did three past questions. We did 2024, 2023, and 2022. Right? So that was in the last class. We look at the last video that we recorded the class. That video was sent in the group. So if you look at those, look at the video of the last class, you see those three questions done. So I'm going to start today now with 2021. So this is the 2021 paper. And as I said, we're just basically focusing on the motion and straight line questions. It is at number 4, because it comes now with the rates of change question, the differentiation and the integration question. That's what I said it now. In the past, it's fit on a question like said. All right, but that's how the set it. All right, so it's number 4. So we're going down to that question. The motion and straight line. This is it. This is it. All right. It says a motorist starts from a point X and travels 60 meters due north. So travel 60 meters due north to a point Y at a constant speed of 4 meters per second. Means that acceleration is 0. And when you're traveling at a constant speed, we can just simply use speed equal distance over time. All right? It says he stays at Y for 25 seconds and then travels at a constant speed of 10 meters per second for 100 meters due south. So that means that he's traveling a straight line. So I'm going north first, and then I'm go south. So he's traveling a straight line. So that's motion a straight line. Calculate the average speed for the whole journey. Calculate the average speed for the whole journey. So to get the average speed for the whole journey, we need the total distance divided by the total time. All right. Or should we do a distance time graph for this? I think we should maybe do a distance time graph. Let me see if it asks for distance time graph. Then we want to average velocity. Oh, and I finished there, so. All right. All right. So this is it. So we're gonna need the time travel, because this didn't mention anything about the time, right? So we're gonna need the time travel. What we can maybe do is also do a distance time graph just to have a visual of everything. So let's break down the motion. So it travels from point X, and it travels at a distance of 60 meters. So let's do a distance time graph of it. So let's put in a y-axis and an x-axis. Well, a time axis and a distance axis. So this is the distance axis. And it's really displacement, right? It's not really distancing, it's really displacement. Time. So displacement is in meters, and the time is in, let's say the time is in seconds. Yeah, meters per second. So the time is in seconds. First part of the motion, it travels 60 meters. So we're gonna put 60 meters here. Let's say this is 60 meters. Right here is 60. All right. So it travels 60 meters this way. And we're gonna do, we're gonna assume that the north direction is the positive direction. So we're gonna say, okay, north is positive, and therefore south is going to be negative. Now I'm doing more than I need to do on this question, but I'm doing it in a way because I want us to understand it. And also they could have asked for a distance time graph. I'm just doing some additional stuff, just in case they ask those things, right? So for this average speed, you need the actual distance traveled divided by the actual time taken. This question don't give us any time, but it gives us information for us to find the time. All right? And because it's traveling at a constant speed, we can simply use speed equal distance over time. Because the speed is constant, right? Acceleration is 0. So when I make this be 60 meters, and so it travels 60 meters at a constant speed of 4 meters per second. Remember, on a distance time graph, speed is gradient. The gradient is 4. The gradient is 4. So it should be the motion for the first part. Right? First part up to 60. But I can say that. And this is where it started at X, but the distance is 0. And it's traveled at 4 meters per second. So the gradient of this line right now is 4. So what we don't know is this time. We don't know how long it took, what that time is. But remember, speed equal distance over time, or we could use a gradient is the speed. And the gradient will be the rise over the run. The run is this time right here, so. But after that. So we could find the time that way. So you can say, okay, what a part of the motion, let's call it segment 1. Right? The speed equals the gradient. And the gradient is 60 over the time taken. And that speed, they said, is equal to 4 in the first segment. That's in the first segment right here. So speed equal distance over time. So the distance is 60 and the time is what we're trying to find. This time, right? So based on this, the time is 60 over 4. If you transpose it, multiply by time and divide another 4. 60 over 4 is 15. That's 15. So you take 15 seconds. So right here says 15. Right here says 15. I'm just doing a distance time graph. They never asked for it, but just for practice, in case they did. We put it broken. All right? That's first part of the journey. So we know so far it's traveled for 15 seconds. Let's read again. A motorist starts at point X, travel a distance, and travel 60 meters due north to a point Y. So when I'm up here, say that Y. Once you're on this line over here, so you're at Y. So once you're down here, so you're at X. All right? So once you're on this line down here, you're at X. Put that to purple. Once you're on this line, you're at X. With displacement is 0. Once you're up here, so you're at Y. Distance is 60 meters. All right, and travel at a constant speed of 4 meters per second. On a distance time graph, on a displacement time graph, speed is graded. But you could work through and say this speed equal distance over time. Now, could I say speed? Could I say speed equal distance over time? So the time equal the distance over the speed, which is what we have here. So distance over the speed. That's what we have here. So the distance over the speed. It's 60 over the 4. The distance over the speed to give us the time. All right, I'm sure you could have done that instead, but I'm just doing the graph just in case they ask you that in a question. Then it says, he stays there for 25 seconds. He stays there for 25 seconds. So it means that the distance wasn't changing. So the graph would now be like this for 25 seconds. All right? Like this. And 25 seconds on top of that becomes 40, right? So you reach 40. Because this length is 25 seconds. I'm put down in purple. That is 25 seconds. 25 seconds. Over here is 25 seconds. So that's where is that now. All right? Still at Y, but the time has now reached 40 seconds. Then it says, it then traveled at a constant speed of 10 meters per second. Remember that again is gradient. For 100 meters due south. So if it's traveling south, it's going in the opposite direction. So it's going to go back towards X. And then it's going to go 40 meters below X. But that's not. So it's going to come down like this. And it's going to go to a point that is down here. Put down down here is 40 meters below us. You can put that negative 40. And the grade of this line is 10. Grade of that line is 10. All right. So this was for segment 1 on the graph. If you want to know, we can know what the time of travel is again by doing speed equal distance over 10 minutes. To know what the time of this travel is. Right? Time equal distance over speed. So we could just divide the distance of 100 by the speed of 10. So that's 10 seconds. 10 seconds. Right? So we know that this journey is over 10 seconds. So right here now is 50. Right there, so it's 50. That would be a distance, displacement time graph. That would be a displacement time graph. All right. So if we're doing for segment 2, let's call over here segment 2 or segment 3 then. Up here says segment 2, constant over here says segment 3. So if we're working on segment 3, same thing. The speed is the gradient. Speed is gradient on a distance time graph or on a displacement time graph. And that now is 100 was negative 100. Right? But if you're working with the actual values, is 100 over this time. So 100 over the time of travel is equal to 10. Because travel at speed, the gradient is 10. The gradient of this segment is 10. The gradient is 10, which is the speed. Using that concept. So the time becomes 10 seconds. Time becomes 10 seconds. Time becomes 10. So the time for this motion is 10. So right here is 10. Right here is 50. I go for another 10 seconds. So after the draw the graph, displacement time graph, that's how it will look. And this corresponds to 40 on the years. I travel 100 meters due south. But if you look at it, it go like this. If you look at it and you have a point X, right? You like it go meters to the north first, 60 meters to the north. And then it comes back 100 meters south, 100 meters south, this way. So it ends up at 40 meters below where it started. That's negative 40. Or 40 meters south. It ends up 40 meters south. All right? So watch this now. To the calculator now. I ask for the average speed. Speed is a scalar quantity. So the average speed is the total distance traveled divided by the total time taken with no direction component in it. So see here, the average speed will be equal to total distance divided by total time. And the total distance traveled is what? What's total distance traveled? 160. 60 go up, go down. 160. 160 meters. And the total time is 50 seconds. And that's what you're working on for. What I work out? I work out to 3.2, right? 3.2. 3.2 meters per second is the average speed. Next part now asks us for the average velocity. The difference is that velocity has direction in it. So you can look at it this way. Speed is distance over time. Velocity is displacement over time. That's the difference. And displacement is distance in a particular direction. So average velocity is equal to total displacement or final displacement or net displacement. It's called the final displacement. Over total time, the time it taken, time taken. So that's why time taken for that displacement. Over time taken. And what is the final displacement? What's final displacement? What's the final displacement for this journey? But they want to plan it to go up and then come back down. What's the final displacement? Displacement is how far you are from where you started. That's what displacement is. This span 40 watts. Displacement has a direction in it. You cannot just say 40. 40 meters south. 40 meters south. So its final displacement is 40 meters south. And the total time is still 50. 40 over 50 equals what? Huh? That's 0.8 meters per second south is the final velocity. I have to give the direction. If you don't give the direction, you're in problems. You have to say south. His final displacement is that he ended up 40 meters south, and the total time for his whole journey is this 50 seconds. That is it. So I have to say 40 meters south. So it becomes 0.8 meters per second south. But the velocity, you have to give the direction. That is it. But understand that? So the ask for the graph, that's how it would look. If you ask for the displacement time graph, that's how it would look. All right? Or don't necessarily Z. Don't necessarily Z. Then come down here, something that Z. Z is 40 meters south of X. That should be a graph. All right, that is the 2021 question on motion as well. They didn't ask anything for that. But good. All right, let's go to 2020, 2019. There was no exam in 2020. So remember, all the other papers already, 2024 already, 2025, 2024, 2023, and 2022. So now do 2021. Let's go back now and look for 2019. Let's look at 2019. All right, 2019. The 2019 apparently was still the old syllabus. Yeah, that question by itself. Motion a straight line. Number 7 and number 8. Old syllabus. There we go. Good. That's the old syllabus. Let's go. A car has stopped at a traffic light, meaning that it is at rest. When the light turns green, it accelerates uniformly to a speed of 28 meters per second in 15 seconds. The car continues to travel at this speed for another 35 seconds before it had to stop 10 seconds later at another traffic light. On the grid on page 25, draw a speed time graph to show the information above. Let's just sketch it out first and then we'll draw it, right? They go like this. The speed time graph. So It accelerates, starts from rest when the speed is zero. It's a speed time graph. So it starts from rest where the speed is zero down here, and it accelerates uniformly, meaning at a constant rate. So you draw a straight line to represent that. Draw it in blue. And it went up to 28 meters per second. And it took it in 15 seconds. All right, here's 15. Right down here says 50. The car continues to travel at this speed for another 35 seconds. So just hold that speed for 35 seconds. 35 on top of 15 is how much? 35 on top of 15 is how much? 50, right? Before it, for another 35 seconds, it reached 50. And then 10 seconds later, it had to stop at a stoplight. So it stop sharply. Stop at a stoplight down here at another 10 seconds, which right here says 10. That's a speed time graph. That's a speed time graph. But we have put on graph paper. But that is how it will look. That's a speed time graph. And that's what I have to draw on graph paper. Let's put down. Huh? Oh, sorry, 50. 10 more seconds are 60. That's my mistake, 60. That's a 10. All right, that's what I put on the graph down there, so, right? And I gave a graph like this. So I guess if I put it, I kind of draw it horizontally, maybe put the x-axis this way and the y-axis up here. So, all right? Maybe that's what we'll have to do. Can we do it this way? So we're going to 60. Let me see if we can reach this. So 10, 20, 30, 40, 50, 60. All right, let's do it this way. All right, let's do it this way. So 10, 20, 30, 40, 50, 60. This is your time axis in seconds. And up here, let's go 10 again, 20, 30, 40, 10, 20, 30, 40. The maximum speed it reached was what, 35? What speed did it go up to? 35. 35 it go up to? No, 28. What, 28? 28 it go up to? 28. So I ran too far. So anyway, let's draw it out in red. Let's draw it in red. So the first segment was that it went up to a speed of 28 in 15 seconds, right? 28 in 15 seconds. So 15 seconds is here. 28 is here. So this is the we're looking at. So it's this point we're coming up to. So you draw a straight line from here up to that. That's the first part. All right. Then held that speed. This is 15. It held that speed until we got over to 50, right? As was 35 seconds. We got over to 50, which is right here. So we hold that speed until we reach over to 50. This line is 50. All right, so coming straight across here. Something like that. Let's do it again. Still shifting, all right. And then it decelerate down to reach 60 right here, so right? 10 more seconds. So straight line down here, so now. That is your speed time graph. All right, let's label this up here, so speed. can label at the top of the graph up here. So speed graph. All right, that's it. Simple as that. All right, what else I wanted to do? Then it says, let's reduce the sketch. Then it says, calculate the distance a car travel between the two stoplights. Distance is area under the graph. You know that, right? Good. So, and between the two stoplights, and from the beginning to the end. From the beginning to the end. So it becomes the area of this trapezium here, right? Put on the dimensions on the trapezium in red. Up here, so is how much? 35. This says 35. Everything across here says 60, as you can see. And in between here says 28, right? Every trapezium is half the sum of the parallel sides times the distance between the parallel sides. All right, so down here, so distance equals area. Distance equals area under the graph. Which becomes half the sum of the parallel sides. The parallel sides are 35 and 60 times the distance between the parallel sides 8. That's what we're working on. Somebody write that out for me, please. And the answer is in meters. Distance is in meters. So if you calculate the area, the distance is actually in meters. It's half the sum of the parallel sides times the distance between the parallel sides. So the parallel sides are this side and the 60. And the distance between the parallel sides is 28. And put on those dimensions in red again. So right across is 60. And the distance in between here so is 28. Between the parallel sides. So the upper trapezium is half the sum of the parallel sides multiplied by the distance between the parallel sides. The distance between the parallel sides is 28. What is the work out to? Anybody work this out? How much? 1330 meters. That's the distance traveled. Calculate the average speed of the car for the calculate the average speed of a car over the journey, giving an answer kilometers per hour. They want it in kilometers per hour. So the average speed is the total distance over the total time, right? The average speed is feel like a T-set question. Equal total distance over total time. Total distance is this distance in meter, but 1 kilometers per hour. We can change them kilometers from now. 1330 meters. What the total time was what? Total time was 60 seconds, which is an hour. Make it easy, man. 60 a minute. Minute, 60 seconds. One thing kilometers per hour can change this to kilometers and then change this to hours. All right. So it becomes 1.33 kilometers over 1 minute. Don't it? 60 seconds a minute. 1330 is 1.33 kilometers divided by 1,000 to get kilometers. And then you're going to divide this 1 minute by 60 to get hours. So it becomes 1.33 over 1 over 60 hours. 1.33 kilometers, 1 over 60 hours. 1/60 of an hour. Whatever that works out to know is the answer. Same as multiply by 60. 1.33 times 60. What you get? Huh? No, it can't be 0.0. So you divide it by 1/60. You divide it by 1/60. You divide it by 1/60. To divide by 1/60 is same as to multiply by 60. What you get? How much? Yeah, that's 1 meter. 79.8 kilometers per hour. And man, next question, I'm still similar to anyone who do already. Nobody is person. All right. See if this question finish. Nope. Here's a nice part. All right, you will doing this part. I'll do question like this. I've done question like this in the last class. So come, take a minute and do this one. I'll put a clock on the screen. So they give you this acceleration. See it here? They give you this acceleration right here. Particle move in a straight line such that t seconds after passing a fixed point O, its acceleration is given by this. It says, given that the speed at O is 10, that means that when at O, t equals 0. So when t equals 0, the speed is 10. All right? And also, when t equals 0, the displacement is 0. All right? It says, find the value of t for which a particle is stationary. Particle is stationary, the velocity is 0. All right? I want me to do this one or no one? No one. Want me to do this one? Now go do it. All right, put the clock on the screen. That's the first part. The second part is for you to the distance of the particle travel in the 4th second. Careful now. The 4th second. Give me like a hint. The 4th second is between which and which time? In the 4th second. If I said the distance traveled in 4 seconds, then the distance traveled in the 4th second. The 4th second is between which two time interval? Between t equals 3 and t equals 4. That's a 4th second. So I want the distance travel between t equals 3 and t equals 4. This is t equals 3 to t equals 4. So that's what you're going to work out for me. And then the question done. Right, you're going to find the values of t when the thing is stationary. Remember, it's stationary v equals 0. So you have to go find what the velocity is. So from this acceleration expression, they will integrate and find the velocity. Right? And then give you this information here. Right? They say the speed at O. Remember, at O, E is equal to 0 and the displacement is equal to 0. And also they're telling you now that also this now, they're telling you that the V is equal to 10. That's what this is. The V is equal to 10. V equals 10. That is for you to find a constant of integration. When t equals 0, V equals 10. You have to integrate the acceleration to get the velocity. And then to get the particle at instantaneous, oh, it's when it is stationary. So when it is stationary, velocity is 0. Stationary means the velocity is 0. Value of t when the particle is stationary. The stationary meaning the velocity is equal to 0. Stationary means that you're not moving, right? So I'm gonna put on a clock. See if we can put up a clock on the screen and give you a couple minutes to do it. Where's the clock? Oh, clock. Um, Stopwatch. Something. All right. I'm giving you 10 minutes to do it. You need so much time? I need so much time. Need so much time? 10 minutes. Start. Well, so, okay. Finish. Second part of the distance traveled in the fourth second. Smith. Smith. Oh, all right, George. Gone. Right. Right to the field. Huh? Again? No, I think this question. No. Displacement can be negative, yes. Yeah, displacement can be negative. It means that you're on the opposite side of O. Displacement. This not going to give a distance, it's going to give a displacement. So distance is the distance between displacement values. Find the distance traveled in the fourth second. Huh? The distance fourth second. The fourth second. But what's so the fourth Okay. Don't put some meaning on it, some meat on it. So we can appreciate a little bit better. Let me work about this. All right. I want to add something to it, which is the velocity time graph for this motion. So we can appreciate this integration business a little bit better. But the integrate to get the distance. All right. All right. I'm gonna pause this and minimize it. All right, let's go. Oh, leave those on the screen. All right. So first part I want is a velocity, right? They want the values of t when it's stationary. So you need to find out what the formula, what the expression is for the velocity. So you can put that equals 0. When stationary is usually when it comes to instantaneous rest. A part that is moving in a straight line becomes stationary in order to turn back, to change its direction. Right? Generally speaking, that's when it becomes stationary. So watch this now. They give us this acceleration. And so the velocity, remember, is the integral of the acceleration with respect to time, right? Understand, right? Okay, differentiate velocity to get acceleration, integrate acceleration to get velocity, right? What I go to that? So the velocity is the integral of 12t minus 17 with respect to t. So you integrate it to normal rate. The velocity becomes equal to 6t squared minus 17t plus a constant of integration, which is your u, your initial velocity, which happens to be the 10 of yourself. But I can tell you that when t equals 0, at O, t equals 0, the velocity is 10. Therefore, the u equals 10. Huh? We call it U. It's the initial velocity anyway. No matter what you call it. I know it's the initial velocity, I'm going to call it U. If you want to call it C, same difference. But really is your initial velocity. Because it is the why is it initial velocity? Because it is the velocity. Why is it? What's going on? This going on? I don't know what's going. Hey, what am I going? All right, right? So it's basically, look, it's a velocity when t equals zero, you know. This one, when t equals zero, it's going to be what the velocity is. So it becomes the initial velocity. But if you want to put c, no problem. In any case, the u is 10, right? So it means that the velocity equals 6t squared minus 17t plus 10. What about that? So it is stationary when the v equals 0, right? Stationary when the v equals, let me make the circle small. So stationary when v, we'll put it in blue. Stationary. And stationary also means at rest. When the velocity is 0. So you put in this equals 0, right? So you get 6t squared minus 17t plus 10 equals 0. So you're solving that. It's factorized nicely. Let's go 3t and 2t. And let's go one the midterm of 14. We'll add the 5% here put up. So let's put 5 over here. So we put 5 here. So 2 here. So that works. I'm not giving 17. That's 10 and 6. I know that number 7. Everybody factorize this? You factorize it, you get it and factorize it? Very good. After you get 60. All right, 60 minus 5. And what? T minus 2. Right, see, that's same, they're both negative. All right. Let's just double check that. So it is 12. That's minus 12 and minus 5. Yeah, that's correct. All right, so we're getting T equals 5 over 6. And again, at T equals 2. That's when it is equal to 0. Now, let me put this in the perspective for you now, so we can appreciate it a little bit better. You see, these two, it will be where your velocity time graph intersect the x-axis. That's what that is. That is what that would be. What I'm going to do, I'm going to make a sketch of that velocity time graph. It's a quadratic graph. It has a smile shape. And it crosses the y-axis at 10 and intersect the x-axis or the t-axis at these two places. All right? So I'm going to draw this velocity time graph so we can appreciate what this really means. Let me draw it down this for you. And then also appreciate this a little bit better. So I'm going to draw the velocity time graph like this. Velocity time. And if I'm sketching this velocity time graph, it's going to be a smile. I draw it in purple. That goes like this. That's how it shape, right? No, these two times is when it is at rest. When it's at rest, let me make this a little bit longer. So go like this. I'm extending that because I want to show the point about when between t equals in the 4th second. 4th second. All right. So what it means, guys, right up here says 10. Right up here says 10. Because we're drawing the graph of v equals 6t squared minus 70t plus 10. That's the graph of it down there. So right here says 10 on the y-axis. So right here says 10. When the velocity equals 0, that's on the x-axis. So these two times that we get is where the graph intersect the x-axis. So right here is 5 over 6. 5 over 6. Right here says 2. Right here says 2. That's the speed time graph. So when in the 4th second is from t equals 3 and 4. So we're talking about up here, so 3 and 4. So we're talking about between this segment right here, so. What do we know about distance traveled from a velocity time graph? Distance traveled from a velocity time graph is what? How you get distance from a velocity time graph? Area, don't you? So the distance traveled is the area under here, so. This area. Under here, the distance traveled. See that? Now, when you have the equation of a graph, how do you find area? We have the equation of a graph. Huh? Or you find area from graphs. Calculus method to find area under a graph. Huh? You integrate the equation of a curve, don't you? It's the same thing you do here, so. If you want to find this area here, so integrate this equation of this curve. Because what do you know about a velocity time graph? Area is distance. Distance traveled is area under the graph, don't it? Area under the graph, we get it by integrating. See that? So to find this area, right, we integrate this equation between 3 and 4. You see the connection? So we're connecting back what we do, right, with calculus that we know. Because if you want area under a graph in calculus, you integrate between the limits. So to find area on this graph, using a calculus method, we would integrate the equation. If this was y equals 6x squared plus 17x plus 10, I want to find the area under here. So we would integrate the y, don't it? But no problem. It is a V graph, a velocity time graph. And we know that distance traveled on a velocity time graph is area under the graph. Area under the graph is the integral of y dx. But this is not y, this is v and t. So it becomes the integral of v dt. See the connection? Good. So that's the connection. So we're connecting everything. So this now becomes the distance where they want. Distance under the graph. Distance on a velocity time graph, distance is area. So the distance is equal to that area under the graph. And area is the integral of the v dt. Because if it was y and x, it would be the integral of y dx. But this is v and t. So it becomes the integral of v dt. So it becomes the integral of v dt. And v is the velocity. And it is 3 and 4. 3 and 4. So that's how we get the area. That's a rationale behind getting the area. You get me? So that's how we get it. So it becomes the integral of the v, which is the 6t squared minus 17t plus 10 between 3 and 4 dt. That's how we're working. All right. So put over here, so becomes equal to, huh? Huh? Yeah, used to be last question in the old syllabus. Used to be last question. So you integrate this first, you go and get 2t cubed. So you get 2t cubed. Integrate if you get 17t squared over 2 minus 17t squared over 2. Integrate the 10, you get 10t. And you go in between 4 and 3. All right, can I run it as make this smaller? So we can make this smaller. And let's plug in the values now. I plug in the 4, plug in the 3 and subtract. You get me? So it becomes equal to 2 times 4 cubed minus 17 times 4 squared over 2 plus 10 times 4. The first bracket is subtract, plug in the 3 next, you get 2 times 3 cubed minus 17 times 3 squared over 2 plus 10 times 2. 10 times 3, sorry. How much? 24.5 meters. No, it's meters. Because the distance is an area fine, but it's distance. Let me show you why that is the case as well. Remember, area on this graph is like a length times width, right? Up here, so it's in meters per second, but that's in meters per second. But the time is in seconds. So meters per second times seconds. So seconds cancel and leave with the meters. See that? See that? If you calculate the area on a velocity time graph, the dimension here times the dimension here. The dimension here is meters per second. The dimension here is second. When you multiply them, the seconds cancel. So you left with meters. So the unit is meters, just the same. So if you calculate the area, the unit is meters. If you calculate an area, the unit is meters. That is it. Let me ask you a couple questions about this graph. They can ask you a couple questions about this velocity graph. So what is the particle doing right here? The particle is moving on a straight line, right? Going back and forth. What is it doing right here? And what is the velocity time graph? What is it doing? And what does that mean right here, so? What happens right? What is happening to the particle right here, so? Right here. Huh? Yeah, but that's a velocity time graph. What does that mean to the particle right at this point here, sir? What that? Huh? It is already moving at a speed of 10 and actually slowing down when the time starts. When it starts the time. Right? It is already decelerated, already at a speed of 10. So when the timing starts, it's at a speed of 10 and it is already slowing down. You see that? No, no, start. It is already slowing. It's already moving. It is already slowing down when t equals 0, right? What does that mean right here in this segment? Right here, so. What's happening there? Speed is cutting down. Speed is cutting from 10 down to 0. So it's slowing down. So right here, it is slowing down. Don't it? And the gradient of this section is negative, don't it? So it's slowing down, moving in a positive direction. Right here, so. It's moving forward and slowing down. What happens right here, so, at this point? What happened at that point? Oh, what happened at the point? It stopped instantaneously to turn. So it turns. So here it's like it go forward, like it going forward and slowing down and it turn. So right just away in the turn. So this I know you know so it turn. Because the velocity become negative. But I agree with that. What happens? What is happening in this segment of the graph? This part here. So what's happening here, so? What does that mean to the part? So? It's speeding up in the opposite direction. So here it is going forward and slowing down. It stops instantaneously, stop speed up. So in this segment here, it's speeding up in the opposite direction. What is the gradient of this segment? What is the gradient right here, so? Negative. Because it's falling, it's still falling. Falling line has a negative gradient. So right there, the gradient is negative. So even though the gradient is negative, the acceleration is negative, don't it? Yes, because acceleration on a velocity time graph is gradient. So right here, so the acceleration is negative. But that negative acceleration, they don't mean slowing down. The acceleration is negative too, you know. The acceleration that means slowing down in the positive direction. And it's a negative acceleration. The acceleration down here, so, right here, so, is a negative acceleration that. But this negative acceleration now means speeding up in the opposite direction. So negative acceleration don't always mean slowing down. Negative acceleration means slowing down if you're going in the positive direction. But negative acceleration means speeding up if you're going in the opposite direction. Because remember now, the gradient up is a negative and the gradient down is a negative. Up also means slowing down, but down also means speeding up. But the gradient negative and acceleration negative on both sides. See that? See that? So we have to be careful. All right. What is that mean right here, so? Right at this point. That's a turning point, minimum point at the graph. What's the gradient at that point? No, not turn back. Not turn back. Turn back when the velocity change. When the velocity change from negative to positive, that's when it turn back. Here's how when it turn back. And here's how when it turn back. It have a speed, so it can't be stationary. It has a speed. What's the gradient at this point? What's the gradient at that point? What's the gradient of a turning point? Huh? What's the gradient at a turning point? Zero. So right here, so the acceleration is zero. Right here, so the acceleration is zero, because the gradient is zero. No. Stop is when speed equals zero. Yes, how when it stop, my boss, when the speed is zero. So stop speeding up. So what does that mean? Is that here is speeding up like my fresh. Stop, slow down. See, it starts slowing down. See that? You know, if you're if you're driving a car, just think of it. If you're driving a car and you're pressing gas, and you're gonna start slow down, you have to take your foot off of the gas. So momentarily, for a moment, you're not speeding up or slowing down. So this when it is neither speeding up or slowing down. So at an instant, it is going at a constant speed, at an instant. So right here, it's when it's changing from speeding up to start slowing down at that point. Very important, this point. You have to understand it. So at this point right here, it is changing state from speeding up. It is speeding up right here, so you know, in opposite direction enough. And right over here, so it starts slow down. In order for you to make that change, you have to really speeding up first in order to start slow down. So the acceleration becomes zero at an instant right here. So it's like you're driving a car, you press gas and you speed up. And then you take your foot off of the gas and put up on the brakes. So you change from speeding up to slowing down. But you're still going in opposite direction. So may I ask some other question now again. So remember, right here, so the acceleration is zero. It's changing state from speeding up in the opposite direction to start slowing down in the opposite direction. See that? Because it's preparing to turn again. That's it, to turn again. In order for you to turn, you have to slow down and stop in order to turn. So look, let's talk about it again now. So, right here, so, if you understand the graph, good light, you can answer the question and visualize it, right? So right here, so, oh, sorry. Right here, so you're slowing down in a positive direction, going forward and slowing down. Here, so you stop to turn. You just stop and turn, see that. Okay, you start going in the opposite direction. Down here, so now you're speeding up in the opposite direction. You press just in the opposite direction now. And then here, so now you're still going in the opposite direction. But you're changing from speeding up, okay, you want to start. You want to start to slow down. So yes or no, you're actually slowing down, but you're still going in the opposite direction. Because the velocity is still negative under there, so. But the velocity is reducing to zero. See that? So it's slowing down. What is the gradient on this part of the graph? What's the gradient over there, sir? What's the gradient over here, sir? What's the gradient? Positive gradient. So acceleration is positive, yes, don't it? That's a positive acceleration, you know. But a positive acceleration, it don't mean it's speeding up. It means that you're slowing down while going in the opposite direction. So even though this gradient positive is a positive acceleration, again, that positive acceleration means that you are slowing down while going in the opposite direction. So again, every time positive acceleration means that you're speeding up. Positive acceleration means that you're speeding up if you're above the x-axis and going in the positive direction. You get me? All right. So what happens right at this point? Turn and start up in the positive direction again. So here, so now, so what I mean, so it stop instantaneously again. And then what happen up here, so now? What happen up here, so? Start speed up and go forward again, forever, and turn back again. Up here, so you go forward, speed up, speed up, speed up. You just continue straight now in the positive direction forever. And not slow down again. Speed up eternally after that. You understand? And that's why they ask for the distance traveled over here. So remember now, this is when it turn back, guys. Over here says when it turn back, under here, so. So we're to draw this motion in a straight line. Up here, so forward first. Then here's how when it turn back. Here, so it turn back. And the turn back can go for a while. And then here, so it turn again. And then go forward forever. See that? You go forward first, up here, so. You turn right here, so. Go backwards here, so the whole I said I go backwards. Go backwards. Turn here, so again. Yes, so when you turn again. And then up here, so it's going to go forward forever. See that? You have to understand all of these things, guys. When you understand all of that from a graph like this, you can appreciate questions and answer them better. So that will be the sketch of it. So I wanted to show you the sketch of the graph so we can appreciate the integrating to find the distance. Because we know that area under a velocity time graph is distance traveled. And you get area under a graph by integrating the equation of the graph. The equation of this velocity time graph is this. So you integrate that equation, you get the area in which that area is distance traveled. You see everything connect up. Good. All right, let's leave that one there. So I'm going to another question. And that is 2019. I took up on 2018. That's what I said. All right. I think you did this question already. So here now they give you the displacement. So you shouldn't have a problem. So now that they give you the displacement, you differentiate the displacement to get the velocity. Differentiate velocity to get the acceleration, right? Good? All right. So come. You have a couple minutes to do this one. So here, a particle moves in a straight line so that its distance S. So remember now, what's the key thing here? So distance S from a fixed point O. Distance from a point is displacement. Distance from a fixed point is its displacement. That's what they're giving you. Right? So instead of saying it's displacement S, they say it's S is the distance from a fixed point O. That's it, it's displacement, but displacement is that distance from a fixed point. Right? So that is it. So they've given the displacement from O. All right. So this is the formula for the displacement from O at time t seconds. So after this, they want the velocity when t equals 2. They want the velocity when the particle is at rest. The time when the particle is at rest. Again, when it's at rest, that's when the v equals 0. That's when it stops to turn. Remember, it's when it stops to turn. About to move in a straight line, that will stop in order to turn. And it stops instantaneously. So I want to know the time when it stops. And I want the distance between the rest points. I want the distance travel between the rest points. Come, let's do this one again. Right? When you differentiate this, we're going to clearly get a quadratic graph again. We're going to get a quadratic function again in V. Not a smile graph we're going to get. All right? So to try this one, come. So I want that. I want those two things. The third thing I want is want the distance between the rest points. I'm going to put on the screen. This one for me, the distance between the rest points. Part 3. Okay, can't put there now. I suppose I can copy them in this device. Excellent. Copy the same thing 2 times. Okay. So I don't want the same thing twice. Did it? Oh, oh, oh. Guess that. Let's see if it asks anything. Nothing. Don't answer. Copy this again. Leave them on the screen for you. All right, there you go. Those are the questions. Them 3 questions there. Come on, about 5 minutes for that one. Come on. Huh? What about 5 minutes for this? Yeah? Yeah, but this one of us going to get better now. Uh, I am really. I need so much time, you know. Because I just have another part of the question, you know. Work it out, work it out. 10 minutes. It's one easy, okay, differentiating. Is that cube up here, right? Here's that cube. This is a cube up here, it's a cube. E cube. Remember last what happens to acceleration? Acceleration becomes zero because it can't go faster. And also on a velocity time graph, we on a velocity time graph, we'd expect to see maximum velocity. No, if your velocity time graph that's my graph, a turn graph. Whereas we are on a turn graph, you have maximum and minimum. At the turning point. So the maximum velocity is at the turning point. You can't go no faster. Right? So if you remember that point, the acceleration was zero, don't have to turn on so that is when it reaches maximum velocity. When the acceleration becomes zero. Velocity is maximum. When acceleration becomes zero. Velocity equals to the velocity distance between the two ways, like US time, and then on the time of velocity maximum. That's easy. That's what I think you have. It's extra time. Easy, you know. Things still. I don't know why the things are unstable. So we only have 2 minutes left. Come on, question super easy, man. Hmm? The distance between. Can you come and do a while ago? You integrate the velocity between it. Hmm? Yeah, man, I did it just a while ago. Integrate the velocity to get the displacement. Integrate the velocity to get the displacement. So you're in the limit. Yeah? It's doing constant. When I integrate in the system, you're not integrating in the system. What's me now? You want to tell between the two response. So come up with the displacement there. So the T right. I see where the vehicle is at those two times. The form of the displacement is up. The probably two by that you say two places greater than the difference. And we have to establish the vehicle of the form of the expression for the displacement already. The schedule where is coming from the board. I wrote that on screen. All right. Back. All right. We're back. I don't know what's happening with this device, but it's a problem. All right, let me go through the question. All right, let's go. All right, let's go. So this one, in the exam, I'm gonna get this, I'm happy because you just differentiate it, right? So question one, the velocity when t equals 2. You're gonna find the velocity first. So see here, find the expression by the velocity first. Velocity is ds by dt. So you differentiate this to get velocity. So it becomes 3t squared minus 4t plus 1. So when t equals 2, the velocity, just plug 2 in this. It's 3 times 2 squared minus 4 times 2 plus 1. This is 12. 12 minus 8 is 4. 4 1 is 5. So the velocity is 5 meters per second. Got that? The next part. The values of t when the particle at rest. At rest, the velocity equals 0. So you put this equals 0. That's the velocity, put t equals 0. So 3t squared minus 4t plus 1 equals 0. Factorize this. You get 3t, t 1 and 1. Signs are the same. They are both negative. Minus, minus. So you get t equals a third. And get t equals 1. So those are the two times when that rest. All right? Now watch this now. Remember now, guys, let's think of it this way. That's a velocity formula now. So if you were to think of the graph of this, it's a smile that is a quadratic. And when it's at rest, is where you cut the x-axis. So you cut the x-axis at a third and 1. That's what this means, you know. We cut the x-axis when that rests, when it turns. Goes to rest instantaneously to turn. If you can make that connection, the question becomes even easier. All right, but let's continue. Next part now says the distance between the two rest points. The distance between the two rest points. So why do you want to know where it is from O when t equals a third and where it is when t equals 1? See where it is. It's asking for this distance and it's actually asking for this distance. So for to sketch a graph. Starts at 1. Better start at 1. And go like this. Right here says a third. Right here says 1. The question is asking for the area and I said, you know. So the distance between two rest points, you know. It going to come out negative, yes. But it just means that it is in opposite direction. Because it is distance traveling in opposite direction. You understand? But what you can do also is find where it is when t equals a third and where it is when t equals 1 on that straight line. And it's going to be the distance between them. Right? So where it is when t equals a third and where it is when t equals 1. So see there? So when t equals a third, the displacement is the plug the displacement formula person. This. I'm write out and copy it down. Displacement is s equals t cubed minus 2t squared plus t minus 1. That's the displacement formula. This will tell you where it is at any time. So when t equals a third, this s becomes a third cube minus 2 times a third squared plus a third minus 1. Finish? Huh? Huh? If what? I don't want to answer that. I don't understand that. One next to that. You like an exam. In an exam, you can't ask about the way how you do it. You have to do what you think. What's the record to? But I thought, you know what? None of you did this? What you get? Negative what? Negative 23 over 27. Okay, good. That just means that it has the left side of O. Then when t equals 1, s equals what? S equals 1 cubed minus 2 times 1 squared plus 1 minus 1. What is equal to? Negative 1? Negative 1. So all that means, guys, is this. All that means is this. So the particle is here first. Look, the particle is like at O first, right? Up here, so it's at O, it's at O, right? You go forward first. You go forward first. And then when t equals a third, it actually go backwards first. Because t equals a third, give it, you go backwards first. You go backwards first. So you go backwards first. So you go so first, you go for the next, the opposite side of O first. To a third. And then it turns. What is the record? It's a negative. It's a negative something around 1. Or it's a negative. Is that this come out to negative 1? Swipe out this. That come out to negative 1. And this come out to negative 22 over negative 22 over 27. Negative 22 over 27, this come out to. Huh? But I get that. All right. So it makes sense. Hold on. Because this smaller than this. This is a smaller body than this, right? All right. That's a smaller body than that. There's something wrong. Okay, if you think of it, t equals a third come before t equals 1. That's when it turns right here. When it turns right here, 2 points. So it's like it go backwards first. It go backwards first. Oh, I see what that. I see what that. When t equals 0, it is already at negative 1. That's the problem. You never start at O. See that? When t equals 0, it's at negative 1. See that? I was assuming it was at O. It never start at O. It starts at negative 1. Okay, so it makes sense now. All right, makes sense now. All right, so it's like t equals, this is O. And it start move from negative 1. So it start move from over here. Negative 1 over here. So and it come forward. It starts from over here, which is negative 1, right? That's where it starts move. It comes forward. And when t equals a third, it reach right. It don't reach O yet, you know. When t equals a third, it reach negative 23 over with negative 23 over 27. That's when it turns. So it turns right here. Turns right here at negative 23 over 27. That's when t equals a third right here. T equals a third. T equals a third. And then it comes back and it reaches negative 1 again right here. So Right here, so, which t equals 1 again, is when they reach back the starting point, where it starts from. You see that? They're asking us for this distance between the two places. That distance between the two places. So, the difference between them. So, negative 1 minus that. The algebraic difference between them. This distance you want. So, you're taking a distance down as to negative 1 minus a distance out to 1. So you can literally do those 1 minus a figure there. The difference between those two figures is the distance between them. You understand that? You understand that? You just have the two of them on the opposite, the left side of O, that's all. But the distance between them, the distance between these two is the measure between these two values, between -1 and -2, or whatever that is. So you can literally take the difference between the two numbers, that's the distance between them. The negative just means that they're on the left side of O. The particle starts to move on the left side of O. But when t equals 0, it was at -1. Never start at 0. Never start at 2. Because when t equals 0, this is the displacement, -1. So it actually started to move here. So here, so when t equals 0 is when it starts. This is when t equals 0. When it starts to move. That's where it was. And then when t equals a third, it turned right here. So before it reached O, it turned -23/7. You know, reach O when it turned. Right? And then they come and they turn again. Oh, you said when it turn again. So actually, I should draw this like this. So you still come and turn again right there. So turn right here, so again at -1. Turn again right here, so at -1. When the time was 1. And then they go forward forever after that. That's what happens. Just at this part, to start, it never start at 2. And that kind of tricky. Kind of create a little, they call it, like a misunderstanding. I never start at 2. But still, the distance between them is different between these two values. The algebraic difference between those. So you can do -1 minus -23/7 if you want. Or the other way around. Whatever the difference between these two values are, you can literally just do 1 minus 23/7. 1 minus 23/7. 23/27. 23/27. Sorry. 23/27. That equals 4/7. 4/27. Keep saying 7. 4/27. But the one is same as 27/27. 4/27 meters is the answer for that. The distance between them. But I'm saying you could have integrated between the negative, between the third and the 1. So I've done that as well. Let's integrate between the third and the 1, because the distance traveled between these two intervals on this graph is this area right here, so. Is the area right there, so. You get me? So you could have integrate to find that area there. Right? And if you come out negative, because you come out negative because you're below the x-axis. Because you're on the opposite, you're on the left side of O. That's why you're coming out negative. You understand me? So, but it will be the algebraic value that they get, the modulus of the value they get, the whole number of value that they get. That is the distance traveled. So this is the answer right here. The distance between the -1 and the negative thing. But basically just 1 minus 23/27. Is the distance traveled in that interval. We could also work out the here and the here, so by integrating. All right. What is the time when the velocity is maximum? Hmm? Let me put it in perspective for you. Watch this now. The velocity is equal to this, right? The velocity is, what's the velocity again? Base, right? 3t squared minus 4t plus 1. 3t squared minus 4t plus 1. Now, second step. If this was y equals 3t squared minus 4x, y equals 3x squared minus 4x plus 1. How you find when that maximum or minimum? You differentiate it. No, how you find where it is minimum, where it is stationary. Huh? You have differentiated and put equal 0, don't it? That's all. When we differentiate this, we find where it is maximum or minimum. When we differentiate this, what am I going to get? No. What am I getting? When you differentiate velocity, what do you get? So velocity is maximum and acceleration is 0. Right? You understand? But in real life, it makes sense as well. Because something is increasing. When you reach a maximum speed, it can't increase some more. Acceleration becomes 0. The question is also talking about right here. You know it from the graph. I don't have to work it out enough. You know it from the graph. It is talking about right here when it turns. That's when the acceleration is 0. That's when the velocity is maximum. Just at its maximum in the opposite direction. Right here, so is the average between these two values because it is symmetrical, the symmetrical graph, the quadratic graph. So the t value here is the average of these two. So it's the average of 1/3 and 1. It's right in between 1/3 and 1. This point is right in between the 1/3 and the 1. Because remember, your axis of symmetry will pass through this line. It divides this equally. So the time is between 1/3 and 1. The average of 1/3 and 1. So you could work it out that way. But if you calculate it by putting the acceleration equals 0, you're going to get the same thing. So I can tell you from now that is the average of 1/3 and 1. And the 1 is 3/3. And you're averaging those two. So it becomes 4/3/2 becomes 2/3. 2/3 is the answer. So t equals 2/3 by averaging these two values. Because it is talking about right at this point, which is the average between those two values. That's a quadratic graph. It still has all the properties of a quadratic graph. So the answer is 2/3, you know, right? Halfway between 1/3 and 1 is 2/3. Let's calculate it. Let's work it out and show you. Yeah? Yeah, that's telling, yeah. If I sketch it and I label it up like this and say, okay, it is stationary, it is the velocity is maximum when the acceleration is 0. Acceleration is 0 only at this point alone. That's the only place on that graph where the acceleration is 0, you know. Right? And what is the time at that point? Right in between the 1 and the 1/3 and the 1. That's the only place when the acceleration is 0. And the velocity is maximum when acceleration is 0. Just that it's going in the opposite direction at that point. That's all. You understand? So see it here now. If you work it out the normal way and say, okay, this is maximum when B is maximum when dV by dt equals 0. What is dV by dt? dV by dt is acceleration equals 0. So you differentiate and put t equals 0. Watch this now. You get 6t minus 4 equals 0. What is it give? This gives t equals 4/6. What is 4/6? 2/3. Nobody need to work it out. Make sense? I want you guys to understand this to that level. Come, I'll do that question before we leave. What time is it now? 7:18. What's that class late? I'm come late. Come half an hour late. I'm come late for 2 hours late, Mr. Man. You know, say that the past students used to be here till like 9 o'clock. And no problem. It's different time now, you know. Boy, that's one can't talk to Caribbean and something again. First time student in my class, I pay merit list them I talk about, you know. Merit list. Pay merit list them talk about. Merit list. Everybody want me the merit list. But no one just want to leave, no one to do the work. But really different, I tell you. Really different. As a teacher, I see the transition of students over time, I tell you. I've seen the transition of students. The students in the past are more diligent, more serious, and them just have a higher standard and just want more out of the thing. And I try, don't blame no COVID, man, and stop the foolishness, man. Don't stop blaming COVID, man. Who knows set on their own standard and I find reason and justification for it. Who know don't play on yourself and and I cut back on our ability. Students come to the same class here, same classroom, under the same program, get the same material, right? And was working towards making merit list. That was the objective, merit list. Whether merit list at the school, merit list at Jamaica, or merit list at the Caribbean, they want to come on a merit list somewhere. They want to come on a merit list somewhere. When you come to class and just want to rush go home. You don't understand the thing fully yet and know I rush go home. You're different, man, may I tell you, you're different. Anyway, this one says a bus start from rest at station A, travel a distance of 80 kilometers in 60 seconds to station B. Since the bus arrives at station B early, it remains there for 20 minutes, then starts the journey to C. The time taken to travel from B to C is 90 minutes at an average speed of 80 kilometers per hour. On the grid on page 27, draw a distance time graph to illustrate the motion. Determine the distance of the bus, the distance from station B to station C. Let's sketch it out. And then we can draw up on the graph. So we want all the components. I'm going to do a graph that we have the right time, right speed, and all of those things. The distance time graph the month. You're going to need the right times for each segment. And let's go again. So, and then you know the average speed from station A to station B in kilometers per hour. So to get that average speed, we're going to need the distance between station A and B and the time. And to get average speed, you need the distance and the time, you divide it, right? Let's see. So this question says, a bus starts from rest at station A. So let's do a little sketch of the graph right here. So the sketch it out and never draw it, right? So start from rest at station A and travel 80 kilometers in 60 minutes. 60 minutes is 1 hour. So you travel 80 kilometers of a distance. I don't know that time. The distance is going to be in kilometers and the time is going to be in minutes. All right, so you travel 80 kilometers, up is 80. Up is 80, here we go. 80 kilometers. And then does it in 60 seconds. So this is 60 seconds, right? So greater this line is the speed. Right? So the speed becomes 80 over 60. Rise over run. Gradient on our speed time graph is speed. So right in this segment, the speed is just 80 over 60. You can't see. You go 80 kilometers in 60 minutes. So it's 80 divided by 60 minutes. And that 60 minutes is really 1 hour. So it's 80 kilometers per hour. Right? Next one says, and the travel to station B. So every on this line is station A. Remember, distance time graph shows distance from 1 point only. Shows where the object is from 1 point. So once you're on this line, you're at A, where the distance is 0. So don't say you're at A. Once you're on this line, you're at B, where the distance is 80. So up at B. See that? Once you're on this line, you're at B. Next part. It says, since the bus arrives at B early, it remains there for 20 minutes. All right, so it stays there for 20 minutes. See there? So it stays there for 20 minutes. And this time, right, so now becomes 80. It stays there for 20 minutes. Stays there for 20 minutes and then start the journey to station C. All right, so I'm going to travel to station C now. So like to go further away. All right, let's see what them say about station C. It said the time taken to travel from B to C is 90 minutes at an average speed of 80 kilometers per hour. So this 80 kilometers per hour is the gradient. The gradient. Our gradient is speed. So you got 80 kilometers per hour. And it got 90 minutes. All right. So you got 90 minutes at 8 kilometers per hour. So you can do a thing like this. So you can go like so. Let me draw it like this. So you're going to go like so up to C. All right, and it's gonna reach C. Take 90 minutes to reach C. So donuts are now gonna be 90 minutes, right? So 80 plus 90 is how much? 170, right? Good? 170. And the grade of this line is 80. Grade of that line is 80. So all we need to know now is what this rise is. So the run is 90. Or what is the rise? What did it rise by? Right? So what do we do? What did it rise by? So this is up to C now. Up here, so we reach C. Extend this up. So up here, so now we reach C, right? Up here, so I C. But we don't know. Huh? I think I must have it over there. So I haven't gone back. They're in this room. Yeah, let's push it away. So see here now. We know so the grade of this line. Over this line, the speed is 80, right? Let's work it out. So from B to C, speed is 80. It means a rise over run equals 80. The run is 90 minutes. You see that? The run is 90 minutes enough. The run is 90 minutes. So this is 90 minutes. So what is minutes? And it's what? 80 kilometers per hour. That 80 kilometers per hour. So the 90 minutes is actually 1.5 hours. You put the time in hours though. See that? Because the speed is in kilometers per hour, you have to put the time in hours. You get me? Good. So the time, the run is 90 minutes. You have it? Let's somebody gonna must. Father, I don't have it. Huh? Yeah. Hold on a second. Hold on a second. We're trying to find that speed, that rise, right? We want to find this rise, that distance rise. Um, so the 90 minutes is actually 1.5, 1.5 hour, 1.5 hours. So that is 1.5 hours. So the rise then becomes 80 times 1.5. What I work out to? 120, don't it? 120. That's 120 kilometers. That's the rise. So you see this? You rise by 120. So you reach 200. A rise here is 120. So you reach 200. So up here at 200. But this rise is 120. From 80, if you had 120 to 80, you reach 200. So that's the graph we're going to have to draw. That's the graph we're going to have to draw. The scale. So you see, when you're drawing distance angle, you will always give you stuff they have to work out. So we have to work out something for this segment. Knowing that gradient. Could I use speed equal distance over time to, up here, so you know. Could I use speed equal distance over time? Can I travel at constant speed? Once something travels at constant speed, you can use speed equal distance over time. Just like you had to, they gave it the time, they gave it the time in hours, in minutes, you have to change it to hours. Why? Because the speed is in kilometers per hour. Kilometers per hour. But understand that? So that's how we couldn't get the time. So that's why you have to draw on the graph. You have to turn side over your assistant, so I can't bother. Can't bother draw. Can't bother time. I don't know if I turn it with this device. Can I turn it? Can I rotate it? I don't know to rotate it with this thing. I can cut it and rotate it. Hold on. I can cut it out and rotate it. Let me see if I can cut it out and rotate it. Let's see if that is possible. Let's see if I can do that. Okay. Let's go again. There you go. Wow. All right. Now we're gonna sketch it. That is it. That is it. That is it. We're gonna draw it. So I'm gonna copy my sketch up the top and just draw it up here. Let's copy this that we drew and that was sketch. And let's put it down down here. So we're drawing that on this graph. All right. So the first segment, let's draw it in red. The first segment is 60, 80, 60, 80. The first point is 60, 80 right here. So 60, 80. So 60, 80. So 60 here, so I see 80 right here. So coming to this point. That's the first part. 60, 80. That's the straight line here. So next segment is 20 minutes. 20 minutes up at the top. 20 minutes up at the top. 20 minutes. Constant speed of 20 minutes. Like this. Then we go up to 170, 200. 170, 200. 170 this. 170 right there. So 170, 200. So 200 right here. So 170, 200 is right here. 170, 200 is right at intersection. So let's go like this now from this point. From this point. Go like this. That is the graph. Simple as that. Yeah? Look at picture. What happened? Oh, change the color too. Oh, man. Thank God. Let's put it back. Team shift, man. All right, that's about. All right, good. That is it. All right, that is the graph. And then we have some calculation questions to answer. So, move this away. This part now said, determine the distance from B to C. That was this distance, 120. All right? Distance from B to C. You could have used speed equal distance over time. So distance equals speed times the time. The speed is 80 kilometers per hour. Speed is 80 kilometers per hour. And the time is 90 minutes. 90 minutes, which is 1.5 hours. They put them in here. So it becomes equal to 80 kilometers per hour times 1.5. It becomes 120 kilometers. That's the distance from B to C. That's up here. Between B and C, 120. Last part now says the average speed from station A to B. The average speed from A to B is the total distance over the total time. So that the average speed from station A to B is the total distance of 200 over the total time of 170. See that? You see from A to B, I don't say it starts A, let's say A to B. Oh, sorry, yes, A to B. But then I'm going to say it's. Then, all right, that's a more. But don't give you that. They give you that. Then they give us that speed. No. It's 8 kilometers. It's just thing there. What's one mark for that? You marks for that? I think it's a mistake. That's too easy. I think A to C them want. For A to B, they gave you the information from A to B. See there? That's information from A to B, you know. So to after that is a mistake. I think I A to C them want. So couldn't never be given 3 marks for that. Huh? Is that? Charity? That's right. That makes no sense. 3 marks. The average speed from station A to station B in kilometers per hour. I must A to C them matter. Could never be A. Eh? So I could never be that. That no make no sense. That don't make no sense. Seriously. I can't 3 marks for it. And this was 2 marks up here, sir. Sorry, that's foolishness. We do A to C, changes to C. Change that to C. Must A to C. Because I have to work out the total distance, right? So distance AC is 80 kilometers plus 120. That's 200 kilometers. And the total time was 170 minutes, which becomes 170 divided by 60 hours. So the average speed, most of them one, becomes the 200 over 170 over 60. Write that out, and that's the average speed from A to C. Distance over time. In kilometers per hour. Say 60. Static people can do this, 200 times 60 over 170 equals. Not working. How much? 70.59. Let's call it 70.6. 70.6. Working. Not working. All right, guys. A question done. You guys need to work on these questions, right? We're gonna want some more work on this. Feel like you need some more work on this thing. Another one question for me yet. Another question. I'm not doing no question yet. All right. So what's me now? The recent what? At least the recent paper them from 2024. I think I need to send it to 2025 paper. So 2024, they in the group. 2024, 2023, 2022, 2021. Just do what them question for me now. But the question that's gonna get the exam is more like those. Not these lengthy, full sum questions. You get me? All right. Huh? Yeah, make some changes. Not sure it. Hold on. What's coming up? Not sure it. Hold on. Hold on. Not sure it. Yeah, we coming. Oh, it's on the computer. Oh, shit. All right.